Check it out now, y'all.
Nano Hub U, online instruction.
Well, welcome to tutorial 4 of week 2. And this homework problem asks you to estimate this ballistic conductance. And this is generally meant to illustrate a point that I guess is implied in all of these lectures, but wanted to make this point more clearly. And that is, when we started in the beginning, I'd said that the standard Ohm's law is that resistance is proportional to the length. But one of the seminal results of mesoscopic physics and nano-electronics is that when the length tends to 0, the resistance doesn't tend to 0. And the correct expression is more like L plus this mean free path that we have written as lambda. And one of the points I made, though, is that the second term represents your ballistic resistance, in the sense that if I put L equals 0, what you get, that's the ballistic resistance. And it might look surprising that ballistic resistance should involve mean free path. Because after all, ballistic means electron goes directly like a bullet from source to drain. Well, in that case, what does it matter what its mean free path is? And the answer is that, well, that's very true. But this resistivity itself is kind of inversely proportional to the mean free path. And so when you talk of ballistic conductors, actually resistivity doesn't mean much. Mean free path doesn't mean much, but the product actually means something. And that is something that is independent of the mean free path. So it's not like the ballistic conductance depends on mean free path, but it's just that in usual large conductors, we talk in terms of resistivity, we talk in terms of mean free paths. And if you wanted the ballistic conductance, which is a property unrelated to mean free paths, you could take that product and get the answer. So here what I asked you to do is, we said that, let's write an expression for this ballistic conductance then. So ballistic means if I want the ballistic resistance, it would be rho lambda over A. And so if I want the ballistic conductance, it would be lambda, it would be the inverse of this, GB. So it would be A divided by rho lambda. And this rho is the resistivity, lambda is the mean free path, and A is the cross-sectional area. So what this problem asks you to do is, it gives you a resistivity and a mean free path, one for copper and one for silicon, and asks what must the cross-sectional area be in order for the ballistic conductance to have a certain value. So I think what it tells you is that the ballistic conductance of a certain conductor is, say, 10 times Q squared over H. Question is, what cross-sectional area do I need to achieve that? And this is kind of important because if you are trying to design an experiment, designed to look at quantized conductance, where one changes the cross-sectional area and gets steps in the conductance, then as I mentioned earlier, it's important that the ballistic conductance be a few Q square over H rather than thousands of Q square over H. So you might ask that given a copper wire, how small should I make its cross-sectional area so that the conductance is a few Q square over H, rather than the millions of Q square over H that you would normally get if you took a normal copper wire. And what would it be for silicon? So this expression then, I could turn it around. Since I'm trying to find area, I could write it as A is equal to GB times rho times lambda. Okay, so all I've done is written that thing around. So now let's put in the actual values that I asked you to use here. So GB is 10 q square over h. And q squared over h, again, we are trying to just do this roughly. So roughly it is 40 microsiemens. So 10 times 40, 400 microsiemens. Micro means 10 to the power minus 6th. So you could write that. Now as far as resistivity then, we got two values. One is for copper. And for copper, the value I asked you to use is 17 nano-ohm meter. Nano means 10 to the power minus 9. And then it's ohms, meters. So that's the copper number. And then the other number is for silicon, where it is, I guess, 1 or 2 micro ohm, rather 200 micro ohm meters. So it is like 2 times 10 to the power minus 4 ohm meter. So those are the, I believe, yes, those are the two values I asked you to use. This is for silicon and the other one is for copper. And for mean free path, again, for copper I had 40 nanometers. And for silicon, I had, I guess, 10 to the minus 6th, 1 micrometer or micron. Okay. So unit-wise, when we multiply these out, you can see the Siemen and the ohm. That's Siemen is the inverse of ohm. So that just cancels out and you get square meters. So, and area, of course, should be square meters. So what do we get if we put all these in? I guess you can estimate roughly what you'd get. For copper, you have to multiply these three things. And I think what I got when we multiplied those out was about 27 times 10 to the power minus 20 square meter. That's what I got for copper. Whereas for silicon, I got more like 8 times 10 to the power minus 14 square meter. That's the number I get for silicon. So that's silicon, number it. And that's copper. Now the first point to note here is that the number you get for copper is a whole lot smaller. And that you might expect, that you're talking about a fixed conductance. And copper, if you have to make it much smaller to get that value of conductance. That's 10 q square over h. And if you, so this is an area. So let us try to write the area as the square of something. So what I mean is, see, you have a cross section. This is the cross section, and what you have got is the area. Now, question is, if you think of it as a little square, what is the approximate dimension of each side? Because that then tells you, gives you a rough idea of how small you need to make it. So if you write this as something squared, you see, so many meters square, then I guess it would be 27 square root is about 5. So 5 times 10 to the power minus 10 meters. You see, and that you'll notice is like half a nanometer. And that is on the order of atomic dimensions. See? So the point I was trying to make, I think I stated earlier, that in the case of copper, the number of modes in the cross section tends to be almost on the order of the number of atoms in your cross section. So if you want this 10 q squared over h, you kind of need, very few modes, of course, like 3 or 4 or 5 modes. And I guess I said 5 rather than 10 because, as you know, it's 2q squared over h once you include the spins. So then you have another, say 5 of those. And then, so you need a cross section that has about 5 atoms in it. And again, roughly speaking. So it's on that order. On the other hand, when it comes to silicon, a semiconductor like silicon, the number of modes is more like 1 for every 10 or 100 atoms. And that you can see if you turn this into times 10 to the minus 7th meter square, and let's say 3. So that's like 0.3 micrometers. 0.3 microns, which is like 300 nanometers. So, relatively large silicon wires, you need relatively large cross sections, will show you quantized conductance. And experimentally, you see, people first saw quantized conductance in semiconductors. It wasn't silicon, but it was gallium arsenide. And since then, of course, as I mentioned, people have done experiments on all kinds of materials, including metals, where using Breck junctions, they see similar effects. Now, one last point, and that's just related, I wanted to make the point that, you see, the expression we are using for G, here, the conductance, we have said is like Q square over H times this M lambda. This is like the number of modes that we talked about. And the picture to remember, though, is that this conductance is actually a function of energy. And usually in degenerate conductors, this del F0 del E, the center of it is somewhere in the band, and the actual conductance represents an average over this energy, and so it is roughly on this value. And so what we could do is roughly think of the conductance at one energy, and that would be representative of the kind of conductance you would measure, especially at low temperatures. On the other hand, if you are talking of non-degenerate conductors, which have a chemical potential way down here, then you see the conductance that you actually measure is extremely weighed down by the tail of this curve and has that exponential factor in it. And so I took here numbers for silicon. I mean, for copper, this is never an issue because copper is a degenerate conductor. For silicon, I took numbers for relatively heavily doped silicon, where one can expect to have a picture that's like this. On the other hand, if you had taken intrinsic silicon, then the numbers I'd have got, and if I just analyzed it the way I did, would not be representative of the number of modes that you expect around here. Because although the conduction is because of these states down here, it is also heavily weighed down by that factor. So the point I'm trying to make is the simple analysis we did here is appropriate for degenerate conductors.